for all the branches. Now what I will do, say I will apply KVL to this particular loop, and the direction of applying KVL and that I have taken, that is clockwise and starting from this node A. Okay, so this is suppose your loop 1. So for the loop 1, as you have seen earlier, by using earlier method, so what I did is that at loop 1, suppose applying KVL, what the equation that we have got is what equation you have got is that if you apply KVL over here, then it will be, as I am starting from here at this node A and I am traversing in clockwise direction, and again I am returning to that node again. So what I consider is that once I face positive polarity for a particular element, so the voltage across that particular element I take as positive. So this first I am facing the positive polarity for this R2 element, so the VR2 I take it as positive, so VR2 is positive. Then I am coming to the element R3, and for that I am again facing the positive polarity over here, so it will be plus VR3. Now again I am traversing and I am coming to this node, means the negative polarity of this element R1. So therefore the voltage I will consider as minus VR1, so that will be equal to 0. So this is the KVL equation while we apply for the loop 1. So here you can see that number of unknowns are 3. Okay, so there are, number of variables are 3. This is VR2, VR1 and VR3. Okay, so there are 3 number of variables. Now you see that once we mention the non-reference node, and then if we put the node voltages, suppose here I am putting the node voltage now, suppose at this node the voltage is VA, and at this node B, the voltage is suppose your VB. Okay, so now if I consider the node voltages V and VB, then what will happen is that for this particular loop we can say that if we apply KVL, applying KVL at loop 1, considering node voltages, then you see over here this VR1 means for this particular resistance R1, the branch voltage VR1 and the node voltage at node A, that is similar, as I have stated in the last slide, means last section that I have mentioned, is that for the node voltage that may or may not be the branch voltage, and for this resistance R1, the node voltage is equal to branch voltage. So over here I can write it as VR1 is equal to VA. Okay, and also you can see that VB over here, and that is also again the node voltage and also the branch voltage of this R3 branch. So what we can write, that VR3 again we can write it as VB. Okay, now if we go for that KVL equation over here, then this KVL equation is also like here you see, that is VB, applying KVL So so applying KVL, what we have got is that VB means so now applying KVL considering the node voltages only. If we consider, then you see first from node A, if we traverse towards, then this is again what, plus sign, so that is plus VR2. Okay, then you come to means first this V plus sign, so VR2, then you come to this one, that is VB, and that VB is again plus over here, so that is plus VB. Then again we traverse like this and we come to this node. So okay, this node is again it is minus, and the voltage across it is VA, so that is minus VA, that will be equal to 0. Okay, so this will be the KVL equation, and from the KVL equation we can see that again this VR2 is nothing but VA minus VB. Okay, so what you can see over here, that once we consider the node voltage for the and if we replace all the branch voltages by the node voltages that I have mentioned right now, all the branch voltages, if they are replaced by the node voltages, then number of variables, so number of variables, so what observation we can get from here is that, it's very important, that is number of variables are reduced while replacing the branch or element voltages that is over here for this particular case, that is VR1, VR2 and VR3 by node voltages. What are the node voltages? That is VA and VB. So you can see that number of variables are reduced. So as the number of variables are reduced, so automatically the number of equations needed for getting the values of these variables are also reduced. So the number of equations needed for the analysis of the circuit is reduced. So is it clear now that means the context of the nodal analysis? I think that is clear now. If any confusion you have, then you please tell me. So just now I am going to the next, that is the means procedure for applying nodal analysis for a particular circuit. So this is the understanding that why the nodal analysis, or how the nodal analysis is superior than the basic method of applying KCL, KVL and element method that I discussed in the last class. Okay. So this represents that why nodal analysis. Okay. Now next I am going to the procedure of applying nodal analysis. So So now procedure of applying nodal analysis or node voltage method. Applying node voltage method. Okay, so for that I am again taking the same circuit, and already you know the node voltage method. So I'm just quickly I will be going through the basic steps of node voltage method. But before that I am writing, I'm just drawing the circuit over here. Again the same circuit I am taking for applying node voltage method. Basically whenever a circuit will be given to you, then that will be given to you in this form. Okay, and for this form of circuit you have to means you will be asked to find out say specific current or voltage for a specific branch or something like that. Okay, so basically this kind of form you will get for analyzing, when means for analyzing the circuit, where this I1, I2, R1, R2, R3, all these values are mentioned. Now whenever you are applying the node voltage method for the circuit for analyzing say the particular requirement, then first you have to arrange or you have to mark some voltages and currents. Okay, so that I am just trying to mention over here what are the procedure, step by step procedure for applying node voltage method. So step 1 is the mark the reference node first. Mark the reference node. So here I have told you earlier the procedure for marking the reference node, but also I want to show you that if you take any other nodes as reference node, then it will be okay, no issues with that, but complexity will be more, and at that reference node selection, that is very important when there will be means whatever I have explained, when there will be independent voltage sources present in the circuit. Now whenever there will be no independent voltage sources present in the circuit, so any node you can take as reference node when there will be no independent voltage source present in the circuit. So as you can see here in this circuit, there are only independent current source present over here, so we can take any node as reference node. So but you have to mark it first. Okay, but choosing the reference node, that is very much important while there will be independent voltage source present in the circuit. But for this case there is no independent voltage source, so I am just taking arbitrarily any node as reference node. So that also you can take. So this is your reference node. Okay, so this is the step 1, that is over now. Now go for the step 2. Step 2 says that mark all the non-reference node voltages. So here you can see what are the non-reference nodes over here. This is one non-reference node and this is another non-reference node. So just directly I am putting the or I am marking the non-reference node as this is just VA, this is just VB. Okay, so the step 2 is over now. Now in the step 3, once the step 1 and step 2 is over, we can go for step 3, that is apply KCL at all the non-reference nodes. So here there are non-reference nodes VA and BV. So one by one I am just applying the KCL. So apply KCL, applying KCL at node A. See over here that whenever we are applying KCL, you know that first we need to give the direction of current. Okay, so whenever I am applying KCL at this particular node, you see that this branch current, that is means that the direction is already given. This branch current direction is already given, but this branch and this branch no currents are mentioned. So first I will put the arbitrary direction of current. Okay, so arbitrary direction of current I am taking over here like this. Okay, so according to this current direction, now we can apply KCL at this particular node A. Okay, so at this particular node A, you just see over here that already whenever we are representing the branch voltages in terms of this V and VB, already we have applied that KVL. In the last slide I have shown you that we are applying KVL, and there we are showing that the branch voltages can be replaced by the node voltages. Okay, so already we have applied KVL. Now I have told you earlier that for solving a particular circuit, what are the basic things are needed, that is element equation, KCL and KVL. Also for this node voltage method, we will also apply KCL, KVL and element equations, but we will go for applying KCL right now, and already we have applied automatically, we have applied KVL while we are considering the node voltage that I have shown in the last slide. So already KVL is applied. Now as we are applying KCL right now, so while we are applying KCL, in mind or mentally we will go for applying the element equation also. Okay, so that you see right now how we do. So at applying KCL, that means while I apply KCL, I consider that current that is going out of a node is positive. So here this current I1 is going into the node, so I1 is negative, minus I1. I2 is going out of the node, so that is why I2 will be positive. Okay, so you can take other convention also. Okay, it is not mandatory to follow the same convention that I have that I consider, that is current going out of a node is positive. Okay, so that is the convention that I take. You can take the other convention also. Okay, so whatever, now there are other two branches which are connected. Let us say this branch if I consider, then you see that direction of current is from here to here. So instead of putting the current that is I over here, I am putting the current in the equation by just mentally calculating the element equations over here. So if I apply element equation for this particular resistance R1, the element equation is what? Current flowing through this R1 is VA minus 0 by R1. This is the element equation, V equal to IR. So that I am just putting over here right now, means by doing the mind calculation or the mental calculation. So current that is going through the R1, the current is going out of the node VA, so it will be out of the node, means that will be positive. So positive, and the element relation, from the element relation or element equation we can write that current is VA minus 0 by R1. So that is VA minus 0 by R1. Okay, so here you can see we have applied the element equation. So you can see inside means in this KCL equation we are also mentally doing that calculation for element equation and we are putting it over here. Okay, and then again you see this current flowing through this R2, that is again going out of the node VA. So therefore the current is positive, and the current by applying element equation the current will be VA minus VB by R2. So VA minus VB by R2. So this will be your KCL equation. So this is also element equation for R2. For this is for R1 and this is element equation for R2. Okay. So similarly we can apply that KCL at node B. So we can apply KCL at node B, and once we apply KCL at node B, then again we have to give the direction of current for which branch, means for the branch for which the current direction is not mentioned. So I am arbitrarily giving this is the direction of current. So over here at this node B, if I apply KCL, then it will be again current going into this node, that will be plus VA minus VB by R2, and this I2 is again going into, okay, sorry, current going into I consider as minus, so this will be minus, and this I2 is current going into the node B, that is over here minus I2, and current leaving the node B, that is this current flowing through the R3. So this will be plus, again apply element rule, that is VB minus 0 by R3. So by this I will get another KCL equation. So you can see that only two unknowns are there, that is VA and VB. So the two unknowns, two unknown variable, two unknown variables, that is VA and VB, and we have so we have two equations to find out the unknown variables, that is V and VB. So this is the procedure. I think you have understood.